All right, so we're live. Welcome back to another fun and exciting episode of Calc 1. I'm your host. All right, so kind of just start out. Let me go to the Elgato. Let's just kind of recall where we were last time. So where we were last time was sort of thinking about the two versions of the fundamental theorem, and the one that we really want to use or think about today is this version. Oops, I wanted a little left here. Okay, one of the versions says that if you've got a definite integral, you can evaluate that simply by plugging in b and a to an antiderivative of the function. Okay, so once you've got the antiderivative, it's basically just an arithmetic problem, right? Nothing too exciting. The problem, the hard part though, is finding the antiderivative capital F, right? If you know that in advance, or for the particular example you're dealing with, it's not too hard to figure it out, then great. But in general, finding capital F is the hard part. So we're going to talk about one of a slew of techniques for finding antiderivatives of functions. Okay. Now, and I say a slew of techniques because those of you who, well, is anybody going to take Calc 2? Yeah? Okay. Yeah, so if you go on to Calc 2, the first sort of chunk of the course would be learning a bunch of these other techniques, right? So the substitution technique is sort of the only one that we do in Calc 1, and then all the other sort of slightly more exotic ones you'll do in Calc 2. Okay, so it's sort of an art form to actually do all these things. But yeah, okay. So so let's just talk sort of finding antiderivatives. Okay, so the methods that we have, would help if I could spell this morning. We really only, at this moment, have one method. Okay, namely that it's something that we memorized or it's obvious. Okay, so what I mean by that would be if it's obvious would be something like x cubed, right? What's the antiderivative of that? Right, okay, so that's just, it's obvious in the sense that it's one of the very basic rules, okay? Or it's something we memorize, like what's the antiderivative of cosine? Sine, right? Because you know the derivative of sine is cosine, okay? So basically, right now, that's the only trick that we have up our sleeve. Now, it's a pretty good set of tricks, right? But it's only the beginning, okay? And so the new technique that we're going to learn is the method of substitution. Substitution. Okay? And another way to think about this is that this is kind of going to be the chain rule, but in reverse. Okay? So it's sort of the antiderivative version of the chain rule. There is also an antiderivative version of the product rule, and that's called integration by parts, and it's one of the very first things that you would do in Calc 2. The quotient rule you can think of as really being a special case of the product rule, right? And so we don't really have a separate version of that one. Okay, So let's just start with a really simple example to kind of motivate it. Okay. Well, first off, what's this? Yeah, e to the x plus our constant as usual. Okay. So that's sort of our basic fact. So if I were to come along and say, let's do e to the 3x. Well, it's pretty close to e to the x, right? I mean, there's that 3. So what might we guess as the answer? Okay, e to the 3x over 3, or even just e to the 3x. Okay, so let's just suppose just for the moment that we guessed e to the 3x, right? Sort of by pattern matching from e to the x, okay? Well, this is the thing about antiderivatives. How can you check whether or not your answer is correct? I mean, other than Edfinity says it's wrong or right, or you look in the book or whatever, right? How can we determine if we're correct or not? Yeah, take the derivative of your answer, your supposed answer, and if you get what you started with, and you were pretty confident you didn't botch taking the derivatives, then you're correct, right? And if you get something different, then your supposed antiderivative is probably not correct. Okay, so if we guessed e to the 3x, and we said, okay, let's check and take the derivative of e to the 3x, and of course, what's the derivative of plus c? 0, because it's constant, so I don't need to really worry about that. What would we get for the derivative of e to the 3x? E to the 3x times 3 by the chain rule. Okay, which is not what we started with. I mean, it's close to what we started with, right? We're just off by a factor of 3. Okay, so then what would we make our new guess? Instead of e to the 3x, yeah, let's do 1/3 e to the 3x, okay? Because when we take the derivative of that, we'd get 1/3 times e to the 3x times 3 by the chain rule, again. But then what happens to the 3 and the 3rd? They cancel, leaving us e to the 3x, which is what we started with. Okay, so we've got it. It's that. Okay, now this was, I mean, I deliberately chose sort of a simple example here, right? It perhaps wasn't too hard to think, oh, it's off by a factor of 3, so I'll just throw a 1/3 out front and that fixes it, okay? But we're going to have to think about this in a slightly more sophisticated way for harder problems. Now, another way you could think of this 1/3 would be, what popped out when we took the derivative of e to the 3x? A 3 popped out, and we multiplied by it, right? Well, in our sort of socks and shoes analogy, what's the sort of reverse process of multiplying by the derivative of the power, dividing by it instead, right? Well, what's the division by 3 is the same as throwing a 1/3 out front, okay? All right, so does that kind of make sense? All right, now, let me show you an example where if we're not careful and we think about it too naively, we're going to get garbage, okay? All right, so I'll continue with this e to the x kind of example. Okay, good? All right, so let's suppose instead we had, oh, I'm sorry, did you guys all, are we good to move on? Yeah, I should have asked that before I do it. Okay. Let's suppose instead that I had something like, well, here. Let me just start with this one. Okay, e to the x squared. Okay, so what might be our guess based on the analogy of the last problem?
E to the x squared over 2x.
Okay. And how did you get that? Well, you said, all right, the antiderivative of e to some stuff is e to the stuff, so we're good there. Okay, what's the derivative of the x squared, the exponent? 2x. And if we were doing the derivative, we would have to multiply by 2x. We're doing the antiderivative, so maybe we divide by 2x. Okay, seem reasonable? All right, how do we check if this answer is correct, though? Yeah, take its derivative. Okay, so let's check that. What is the derivative of e to the x squared over 2x? Well, what are we going to have to do here? Quotient rule, and also in that a chain rule. All right, so it's going to be the bottom thing times the derivative of the top thing. Well, what's the derivative of e to the x squared? E to the x squared times another factor of 2x. Okay, minus, so we did bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom thing squared. Okay? And then at this point, we'd want to do some simplification if we could. I mean, it's clear right this instance that this is not obviously equal to e to the x squared, but maybe with some simplification it actually is. Okay, well, so let's clean it up. So what do we have? We have 4x squared e to the x squared minus 2e to the x squared all over 4x squared. Can I just magically cancel those 4x squareds? Nope. Or maybe actually one other thing I could do is I could actually break the fraction up and cancel them, but then I would have that. Okay, and the reason I wrote it that way is because we can see, oh, well, there's e to the x squared. That's good. But what do we have? Yeah, we've got this, right? We've got some baggage left over, and it's not just disappearing. Okay, so what's the conclusion that we're forced to accept here? That ain't it. Our guess was wrong. Okay, now, why did this break when it worked perfectly well for the previous problem? The reason is what's the derivative of x squared? Not just 2. So it worked in the previous example because the derivative of the insides was just a constant. The derivative of x squared is most certainly not a constant. Okay, so that's why this broke. Okay? All right, so this was bullshit zone. Right, this is why I wrote naive guess. It's also fun because it means I can put the umlauts on the I. Yeah. Huh? You don't put umlauts on things?
On I, no.
Well, because this is a French word, not a. Okay, so, all right, so that's not going to work. So we got to do something a little bit more sophisticated. Okay. Now, the other reason that I picked this guess is because e to the x squared, if we think about it, this was an example of one of the things at the very end last time, which is I happen to know that we cannot express the antiderivative of e to the x squared as an elementary function. Okay, so no matter what voodoo I do, I'm never going to get an answer to this that's going to be something that we could just write down. Okay? So I picked a sort of deliberately impossible problem to force the issue. Okay. Is that all right? Okay. But let's go back to the e to the 5x example, okay, and kind of work through the slightly more sophisticated way to think about it. Not because we need to in that particular example, but it's simple enough that we can start to see the sophisticated approach, and then we'll throw the sophisticated approach at a problem that's not so obvious. Okay, Gucci? All right, am I cool to move on the screen here? Yeah, Owen, good, okay. All right, so let's go back to, the original example, okay? Oh, by the way, what's going on the mall today? Are they doing like a food truck or something again this afternoon, or? Huh? Well, because they've got half the mall coned off. I mean, this is one of the advantages of getting here before 8, is that for the most part, you get whatever parking you want, unless freaking Austin Shivington has left his car out there. I've told you guys about my blood feud with Shivington, right?
No, you've not.
I haven't? Oh, so do you guys know what Austin Shivington drives?
No.
Okay. He drives a Mazda 3 hatchback. It's white. What do I drive? A Mazda 3 hatchback that's white. Okay? Now, his is the sport model and a manual transmission, and mine is the regular working dude model with an automatic transmission, because I actually don't know how to drive a stick. I wish I did, but I don't. And so when I pull onto the mall and I see his car, I'm like, Shivington? Particularly if there's not a space for me to park in, right? Like if there's a big space behind him, it's really cute, because then we've got 2 Mazdas in a row, right? There was one time, this was maybe a year or 2 ago, it was in the before times, that's for sure, that I'm pulling, around the mall to go home, and somebody just runs up and like they nearly run in front of me, and I almost hit them. And I'm like screeching to a halt on the brakes, and I roll down the window and I'm like, well, what are you smoking, dude? He's like, oh, I thought you were Austin. I'm like, same car, different person. And he's like, oh, I'm sorry. I'm like, you really shouldn't like basically leap out in front of cars, right? Because, if I had been going a little faster, I might have actually not been able to stop in time. So, yeah, that was a weird experience. All right, anyway. But there was this parking spot for me today, so all's good, right? All right, so e to the 3x, right? We already know what the answer is, but so let's concentrate more on the method. So if this had just been e to the x, we wouldn't have needed to do anything, right? It would have been obvious. The problem is it's not, okay? So what I'm going to do is I'm going to say, let's turn the 3x into just a singular item, okay? And I'm going to call this u, whatever, okay? I could pick smiley face for all I care. It doesn't really matter what letter I pick here, with the exception of I can't pick x because I've already used it, okay? All right. What's wrong?
You should use O.
O?
That's very.
No, that's like the worst variable because it looks too much like 0. Yeah. Okay, so then what I want to do is I want to write what is the derivative of u. Oh, no, sorry, just u. The function that we're dealing with is e to the u. You're right. Okay. All I want to know, though, is what's the derivative of u? Huh? Okay, let me rephrase. What's the derivative of u where x is the variable? So symbolically, it'd be du dx, and then the answer is, huh? Did you just say 6?
No, 3.
3, okay. Right. It's a good thing it's Friday. 5, 3, sir. No? Do you guys know what that's from? No? Monty Python and the Holy Grail, when they've got the holy hand grenade of Antioch, right? Thou shalt count unto 3, not unto 4. 5 is right out. Yeah, anyway, okay. So 3, we're good? All right. So the next thing I'm going to do, and this is going to feel a little slimy, is I'm going to, okay, don't think about what I wrote just there as if I was treating du over dx as a fraction. Okay, is du over dx a fraction? No. Does it look like a fraction? Yes. Okay, and that's kind of a misleading notation that we use, right? Because it's not really a fraction, but in some cases we can sort of pretend it's a fraction and write du is 3dx. Okay, now we haven't really talked about differentials, okay, but du by itself is what we call a differential. Dx is also a differential. We'll talk about those things more later in the semester, but for now, just humor me, okay? Now, but that said, we shouldn't be too bothered by having lone d whatevers around, because what is there in the integral? There's a dx, right? Now, what did dx mean when we were sort of setting up the integral? It was kind of the width of rectangles was what that meant, okay? So just humor me here, okay? And then let me take this, and I'm going to solve that equation algebraically for dx. Right now I have du equals. I'm going to rewrite it so that I have dx equals. In this case, that's really easy. I just have 1/3 on the other side. Okay, so does that kind of make sense? Okay. Now at this point, what I'm going to do is I'm going to say, well, I called 3x by the name u. Great. I called, and then after we defined that, we saw that dx was 1/3 du. Okay, well look at the two pieces of the integral that I wrote. The blue box, what am I going to replace that with? U. Good. The red box I'm going to replace with? Yeah, exactly. Okay? All right. Pro tip. How do you know if this process has gone horribly wrong? Is after you do that substitution and maybe a little bit of simplification, there's no simplification we need to do in this example. Are there any x's left? No, everything's now in terms of u. Okay? If this has gone horribly wrong, after you simplify and there's still both x's and u's left, you've probably chosen a bad value of u or screwed something else up. Okay? Now, in this case, no worries because, well, 1/3, right? Nothing special there. Okay. But can I do this? Can I just pop that constant out front? I can, but let's make sure that we're cool as to why I can do that. Okay? I can pop the constant out front for the same reason that I can do that when I'm doing derivatives. So if I know what the derivative of a function is, and then I ask you what's the derivative of 5 times that function, what do? You just do 5 times the answer you already know, right? So if it's a constant, which 1/3 certainly is, then it works there for antiderivatives the exact same way it works for derivatives, right? No biggie. Oui ou non? Okay, très bien. Okay, now, do we know what the antiderivative of e to the u is? It's just e to the u. Okay. And then, of course, we've got our handy-dandy plus c there. Are we finished? Yes and no. Okay, so we're basically finished, but not quite. What's the one thing we still need to fix? Replace u. Okay, the original problem had no u's in it. That was something we chose as an auxiliary tool. So I need to replace it with what it was. Okay, so maybe cheesy analogy here. Let's say you're, I don't know, you bought a new bookshelf for your room. Okay, you need to put the bookshelf together. Probably you're going to need a screwdriver or something, right? So if you go and you borrow a screwdriver from your dad, and then you don't put it back when you're done, what's going to happen? Huh? What? Oh. Well, maybe your dad's a nicer guy than mine, but no, I mean, you get busted, right? You put the tool back when you're finished using it. Well, same thing here, right? Put the tool back when you're finished using it. Okay? All right, so does that kind of make sense? All right, now, after you guys get good at this and have practiced, particularly once you get to Calc 2, if the only issue is the constant, so like the 3 or the 1/3 kind of issue here, that I would expect a Calc 2 student to be able to do in their head and go directly from the start to the finish. Okay? That takes some practice. Okay? So for the meantime, go ahead and even though it's not perhaps absolutely necessary in this example, go ahead and go through this whole process with the u because you'll get more comfortable with the process, and then when you have to do a problem where it's absolutely crucial to write it all out, then you won't be boned. Okay? All right, so let's return to the e to the x squared example and see another reason why this fails. Okay? Or sorry, why that one doesn't work out. All right, so let's go down here. Okay, what would I guess here for you? What's probably our only choice? Yeah. Okay, and then du is 2x dx. Okay, well, actually, you know what? Let me put one step in between there. Okay, so what's the derivative of u? Du dx is the symbol for that. And what is it in this case? 2x. Okay, so we Gucci with that part? Yeah. And then I just sort of cross-multiply this thing like I did before, pretending for the moment that du over dx is a fraction. But then I'm going to say, all right, solve that for dx in terms of du. Okay? So is that all right? Now, let's make the substitution. Okay, so I would have e to the u, dx is du over 2x. What's the problem? Yeah, we got both u's and x's. And is there any way that that x that's hanging out there, does he cancel with anybody? No. So we're hosed. Okay, now, here's a very common mistake that I found over time students will make. What did we do with the 1/3 in the previous problem? We just popped it out front. Okay, so let me write that's the mistake that will happen often is, well, if I can move constants out front, I can move anything else out front. Not true. Okay? You can move constants out front, but things that have variables in them, ooh, bad, 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 bad dog. Okay? You cannot do that. Okay, so do not do that. What this means, if you get to a point like this where we're stuck, is that the substitution you have chosen is not the correct one. Okay? Now, if we look back at our original problem, though, was there really anything else we could have picked? No. So this might clue us in that this is actually an impossible problem. Okay? Or, maybe better put, it's not possible to do it with the method of substitution alone. Okay, maybe there's some clever thing that you learn in Calc 2 that would let you do it, but this is not one of them. Okay? In fact, there is no answer to this, as we've discussed. Okay? All right, so let me change the problem so that we actually could do it, and we'll kind of look at it again. All right, is that okay? All right, so am I good to move to a new sheet? Yeah, okay. All right, so instead, let me put another x in the original problem. Okay, good. So, is this something that we just happen to have memorized, what the antiderivative of x e to the x squared is? Most certainly not. Okay? And so that means the only other option is to try this substitution method, because that's the only other trick that we have now. Okay, but we have a choice here. What are we going to make u? What are our two choices, perhaps? X and x squared. Okay? All right, now I'll give you a hint. Letting u equal x, u is the stupidest substitution you could ever make, because all it does is it turns the problem from x e to the x squared dx into u e to the u squared du. Well, what did we say about x and u? What kind of variables were those? What did we call them? Dummy. Does it really matter what the symbol is? No, it could have been e to the smiley face, or sorry, smiley face e to the smiley face squared d smiley face. Means exactly the same thing, right? So letting u equals x is the absolute worst substitution you could ever make because it's useless. It doesn't change anything. Okay, so if our two choices, potential choices, were x and x squared, and I've just said that choosing u equals x is the stupidest thing imaginable, then what? Yeah, we're kind of fresh out of options, right? So let's just let u equal x squared. Okay, now, in this particular example, or the other ones, it was pretty obvious what to make u. As the problems get a little bit spicier, right, as we move up the Buffalo Wild Wings spice hierarchy, it becomes sometimes less obvious what u is. okay? And in the course of working exercises, you guys will start to develop a spidey sense for what's a good choice of U and what are bad choices of U. Okay, that's something that comes and is developed by experience, not by anything else. Okay, so, right. Okay, so this is maybe another thing about antiderivatives. Doing them is really kind of an art form. Okay, whereas taking derivatives was mechanical. Right? If you knew the three rules, product, chain, quotient, and you knew all the basic definitions, and you could just execute, instructions on a piece of paper, might take you a while, but would you eventually get the correct answer? I would hope so. Okay. That is unfortunately not really the case for antiderivatives. Is that it's not as formulaic. Okay. And so the tricks and the techniques and what you pick to be U and so on, right, are things that you will get with some experience by practicing lots of these things. Okay. All right. So we said U equals x squared. So what does that make du dx? 2x. Right, that's just the derivative. And so du is 2x dx, and therefore dx is what? 1 over 2x du. Okay, so we're cool with that part. We? Okay. Now, let's substitute. What did I call x squared? U. Dx, I just said, was 1 over 2x du. Okay, now, at first glance, you might say, wait a minute, Dr. McKinney, you said that x's and u's in the same thingy was verboten. Okay, but what can we do here that we couldn't do in the last one? Yeah, we can combine and simplify things, and in particular, what happens to the x's in this case? They cancel, and so what we're left with only has u's in it, and this constant, okay? All right, is that all right? Okay, so just simplify it first, and if there's still, after you've done all the simplification that's possible, there's still both x's and u's, then you've probably chosen a bad u. Okay, the things did simplify here, so we probably picked a good u. All right, now what's the antiderivative of e to the u? E to the u, and I've got this a half out front, so no big deal there. Oops. And what was u? Like that. Okay, there we go. Okay, so is this process kind of starting to make some sense? Yep. Okay, so how do we know that this answer is correct? Take its derivative. Okay, so do that. Sit down and write down its derivative. Okay, so this is the check step. This is usually the part where you pull out paper and start. You don't have a pencil? Well, you don't seem to have any paper either. Oh. Well, you know, if only your dear professor had his backpack here that is laden. Yeah, laden with pens of various colors. Heck, I've even got a flashlight.
Could I use the flashlight?
No. Well, I don't know. Do you want to illuminate how calculus works? Then use I know, right? That was totally a dad joke. Huh? Yeah. Now, you guys might ask, why do I carry a flashlight in my backpack? That's maybe a better question.
It's dark, right?
Huh? Okay. Well, I mean, I carry a flashlight. I carry a knife, right? Huh? Well, you don't carry like a pocket knife or a Swiss Army knife or something? Oh, well.
Got lots of things.
Huh? No. Taking a knife to a gunfight is usually a bad idea. No, the reason I really started carrying a flashlight is because many semesters when I'm teaching calculus, we actually are over in the hazement, okay, the basement of Hayes, right? And more than one occasion, the power has gone out, and it gets very dark down there. And so I was like, after the first time it happened, I'm like, I really should put a little flashlight in my bag just in case. And so I got this little guy on Amazon, and it fits great in the bag, and yeah. So anyway, plus I can illuminate the calculus. Okay. All right, so what'd you guys get? How does this work? The derivative of 1/2 e to the x squared is 1/2 e to the x squared times, because of the chain rule, the 2's cancel, and we're back to where we started. Okay, so good. We did it. We double checked it. It worked. Everything's fine. All right, so does this kind of make sense? Yeah? All right, so let me do maybe one more example, just to spice it up a little bit. Let's see, which one do I want to do? I know. We do this. Okay, so this one I'm going to have to be a little bit more clever on. All right, so what would be your potential choices for u? Okay, we've already established that picking u equals x is stupid. Okay, so let's no longer list that as a choice in the future. Yeah, we could pick 1 plus x to the 4th, okay, the entire denominator. We could pick x to the 4th, okay, or, this is going to seem a little crazy, we could pick x squared. Okay, where did I get x squared out of this? Let me rewrite this slightly. Can I say that? Okay, so if you will humor me and take my word for it, the correct choice here is actually x squared. Not x to the 4th and not 1 plus x to the 4th. Those were reasonable options, but they're not going to work in this particular example, okay? And so let's just kind of go through it and see why. Okay, so if I do all the derivative stuff, substitute in, okay, what happens to the x's? They end up canceling. And so I've got 1/2, that's just a constant, so I can put them out front. 1 over 1 plus u squared du. Okay, and so it might look like, wait a minute, Dr. McKinney, that has not really helped matters, has it? Except, do we happen to know about 1 over 1 plus u squared? What is that? Exactly. It's the derivative of arctangent. Okay, so we do still have to remember all of our basic ones. Arctangent is maybe the most spicy of the basic ones. Okay, and then what's the last step? Yeah, substitute back in. Okay. Now, if the original problem had been x cubed over 1 plus 4x squared, what would have been a good choice for you? Or sorry, 1 plus x to the fourth in the bottom. So instead of x on top, what about if it was x cubed? Then I would have picked u equals 1 plus x to the fourth, because what's the derivative of that? It gives you an x cubed, right? So what you want to be sort of sniffing out here is that a good choice of u is where you make some of the stuff u, and the derivative of that is the other stuff left over in your problem. Okay, that's sort of the goal. Okay, but it's all right. If you choose the wrong u, what's going to happen? You'll get stuck a few steps later. All right, well, go back and try again. Okay, there's only so many options that are reasonable, because as we've said, u equals x is stupid. Okay, so don't pick that one. There's only a few other really options left here. Okay, and by doing a bunch of these, like I said, you guys will get your spidey sense. All right, now, one last thing. U substitution is hard. Okay, and it requires some practice. All right, so I want you guys all to think of a number between 0 and 100, okay? But not just any number, you're not picking it at random. If 0 to 100 was the scale of a grade that you could get on an exam in calculus, what would have been the grade that Dr. McKinney got when he was in calculus on the exam that was full of u substitution problems? Okay, so we had our u substitution test. Dr. McKinney took the test like everybody else. What grade, 0 to 100, do you think that Dr. McKinney got? Okay? 102. Somebody's sucking up, right? Okay. Well, and let's also go with the assumption 70 to 80 is a C, and 70 is sort of passing, and right? What did I get? 54. Yep, I bombed it. And you know why I bombed it? Well, yes, but I also hadn't done enough homework and hadn't practiced enough. Okay? Now, you guys like to, maybe it's a reasonable assumption to think I was pretty good at math. But I did end up as a math professor, so right. All right, so if Dr. McKinney can fail one of these things, what might happen to you guys? Well, you won't pass the assessment, right? I'm doing it a little differently. But practice this stuff, guys. You'll be rewarded if you practice, okay? All right, so, the other thing, just to make sure we're clear, are we doing an assessment on Monday? No, we'll do it Friday next week, so don't freak out. Yeah. All right, have a fantastic weekend.